Okay, all right. So we are continuing on covering, I guess, hierarchical models and the Gibbs Sampler. So I think we left off on Wednesday. We had coded up a Gibbs Sampler in R. I don't know if, I'm not sure if we ran it or maybe we did, but basically, I think we ran it. This is our hierarchical model. We said K is just some arbitrary constant. Omega, which is going to be, which is used to determine alpha and beta, is drawn from a beta distribution. And based on omega and K, we will get the shape parameters alpha and beta for our prior distribution. Alpha and beta go into our prior distribution for theta, and then theta gets used in a Bernoulli distribution to determine the outcomes y. And we ran this code in the, we wrote a lot of this up right here. And so, we had simulated some data. I just kind of arbitrarily set this up. I have a proposal function, a function to evaluate probabilities, because this is going to be, we're combining Gibbs Sampler with the Metropolis algorithm. And inside, this is the primary loop here. What we do is we have the Gibbs Sampler running here, which is drawing values from a beta distribution after we've updated it. So this is drawing theta values from the posterior distribution, where you take alpha plus the number of hits and beta plus the number of misses or outs. And so so you have that, and then to sample values of theta, we use the Metropolis algorithm, and we ran that. It takes a moment to run, and did this not run here? Okay, so here's just kind of a plot of the different omega values. And we can see, omega is centered around 0.28. We can ask for quantiles of omega, and we get values between 0.26 and 0.301 from the 2.5 to 97.5 percentile, with a median of around 0.281. Okay, so this was writing up the Gibbs Sampler ourselves, and I hope this feels okay. I don't know if there's any confusion or questions about this so far. And here I wanted to introduce this system, Jags. Okay, so here's just more diagrams of how it works, right? So from the hyperprior, which is a beta distribution, we draw omega, which determine what alpha and beta are. Those go into the beta distribution, which determine the thetas. And from the thetas, we put those into the Bernoulli, and that samples the individual hits and outs. So I wanted to introduce Jags. Jags is kind of this system where you can, where it performs Gibbs sampling. And one of the nice things about Jags is you don't, if you use Jags, you can, you just need to be able to specify the hierarchical model. Okay, you specify this hierarchical model like this, and you don't have to go through the process that we went through on Monday, where, so on Monday, if I pull up the lecture notes, we had to figure out what the, we had to, kind of factor everything out into different distributions, okay? And so, we had to say that our beta distribution would look like this, and we would have to figure out the posterior distribution. We had to do that on Monday. With Jags, all you have to do is specify kind of the hierarchical model, and it will take care of the rest. which is nice. And so Jags is a separate program, and you can interact with Jags using different interfaces in different languages. So you can interact with Jags from, say, Python and things like that. Whereas we're going to be interacting with it via R, and there's a program called R2Jags. There's other libraries. There's RJags, and I don't know, a couple other things that interface with Jags. And you know, I'm using R2Jags, but there's others out there. Okay. So the only thing about Jags is that you've got to be able to specify the model. The model is specified using the bugs language. Okay, so JAG stands for just another Gibbs sampler. Bugs was Bayesian inference using Gibbs sampling, and it has you know, this language that looks kind of like R, but is a little bit different. Okay, and you can visit their kind of documentation for what the what distributions exist. So you can get values from the log normal, from the logistic, from the normal, and things like that. And they're all kind of written like dnorm and dunif and stuff, values that are familiar to us. But unlike R, when you call dunif or dnorm or things like that, R would take in kind of the value of X, and then along with the parameters, and return the density. And here it doesn't take in an X, you just give it the parameters. Okay, so I don't know what this slide is. Okay, so our model in the bugs language. So if I go back to this slide and this slide, okay, this is how we would specify the model in the bugs language. Okay, so we have a matrix Y of our data, and what we're saying is that we have n players, okay, and the players will be indexed by S. Okay, so you know, for player S, okay, player S has their own theta value. Okay, so we've got theta, you know, bracket S to indicate, you know, we want the S value of theta. So theta is a vector of batting averages, one for each player. Okay, and we're going to say theta for player S is drawn from a beta distribution. Okay, and so we use kind of the tilde symbol to say that it comes from the beta distribution, and so we say d beta, and then the beta distribution has two shape parameters, alpha and beta. Okay, now the weird thing is that this thing is all kind of wrapped up inside a function. Okay, now this is not a real R function, and if you try to run this like a function, it's going to error out because there's nothing like this. Looks kind of like R, but it's not. Okay, so you know, bugs was designed kind of by an R user, so there's a lot of similarities to R, but this would error out if you tried to, like, we don't have this. Well, I mean, we have this symbol when like setting up a linear model and stuff, but it's not used to indicate that, you know, a variable comes from a certain distribution. So anyway, we say theta comes from the beta distribution, and then remember Y are individual hits and outs, okay, zeros and ones. And so we're going to say that inside matrix Y in row S, column J, which indicates whether it's a hit or not, that value comes from the Bernoulli distribution, okay? Bernoulli distribution with parameter theta S. So actually the Bernoulli distribution, there's no dBern in R. And so this is something that's unique to the bugs language here. But we're going to say this comes from a Bernoulli distribution where the parameter is theta S, the theta S for this player. Okay, and this, it goes through it's going to go through this for all of the n players. We also specify and say omega comes from the beta distribution, and the beta distribution is determined by parameters a omega and b omega, which we specify down here. Okay, and so one thing that might strike you as odd is that I'm using parameters and stuff that I don't define until later, right? Because we know if we did something like this in R, this would error out because it would say, I don't know what a omega is because a omega is not defined until down here. But in bugs, it's fine. It reads through this whole thing. It figures out the dependencies between the values, and it's fine that these are not specified in order. Okay, so this beta distribution is determined by these hyper parameters a omega and b omega. Okay, and then the alpha and the beta, so this alpha and this beta, which go into here, these are determined by using omega and k. All right, and here we've just kind of arbitrarily stated k is 300. Okay, so I know it's a little disorienting that these things are all out of order, but we have alpha is set by omega times k minus 2 plus 1, and beta is set by 1 minus omega times k minus 2 plus 1. And so those go into here at into determining this beta distribution here. All right, and so this is kind of how we could specify this hierarchical model, or this hierarchical model using the bugs language. So this would be equivalent to kind of drawing that picture. Is that okay here? All right, and so yeah, again, this just kind of breaks down what we wrote here into kind of sections. And so again, when you specify it, you wrap it up in a function and you put everything inside, and it's not like an R function. Okay, now you can also write just a separate text file with just basically the model looking like this. So that's also possible. Okay, and then yeah, so I think I discussed all of this, but basically each player's theta value, theta sub s, or its subset to s, is comes from a beta distribution with shape parameters alpha and beta, which will be defined later. Each hit, the y's, is a 0 and 1, and those come from a Bernoulli distribution determined by theta sub s. Okay, and this again is j cycles in for 1 through the number of at-bats that player S has. And then omega is kind of gets used to determine what alpha and beta are, and that comes from the beta distribution. And then these define the parameters that we get that are going to be used. Okay, there's other things in the code that I'm going to run. Okay, so here's the model that I've specified. Okay, and then there's other things that I need to include. So when you run Bayes, when you run Jags to fit your model, okay, Jags takes in several parameters. You have to specify the data. You have to specify how to initialize the values. You have to specify what parameters you're going to save. And you can also specify other things like the number of chains, the number of iterations, how many burn-in values you should have, and then basically where the model is stored. Okay. So I'm going to go ahead and just wipe out my my environment here. And so the data that we've simulated, just load up R2Jags. So this is our simulated data. So I've got 10 players. These are their number of at-bats. And this is their number of at-bats, and this is their number of hits. And if I take kind of their batting average, okay, these are kind of their batting averages. So player 1, 118 hits, 486 at-bats, batting average of around 0.243. Player 2, 139 hits, 493 at-bats, batting average of 0.282. Okay, so these are total number of hits. we can look at the actual hits and outs, which is how I've done it. So I've got so player 10. Let's look at their first 100 at bats. So their first 100 at bats is, you know, misses and a hit and misses and a hit and things like that. Okay, and so here is the model that I'm specifying. And again, it's stored as a function in R, but it's not. And then, and again, to run Jags, I need to specify all of these things. So the data is going to be a list. It's a list of objects that exist inside my environment. Okay, so we are going to reference the matrix Y. Number of at-bats is a vector. Okay, this is a vector of how many at-bats we have. The number of players is just a number. It says we've got 10 of them. Okay, but these are numbers that are going to get used inside the Bayes model. So these are values that are not specified within here, but n players in order. So anything that is not kind of created inside the model function, we've got to be able to provide it. So number of players is the number 10. Number of at-bats is this vector of how many at-bats there are. And then Y, which is our data, is, you know, this matrix. This is just one row in Y, but that has to get provided. So we provide it with a list of character names, okay? And then it will know to look up those objects inside the environment. The parameters that we are keeping track of, okay? So we want to keep track of the omega values and the theta values that get sampled, okay? So we're going to create a vector of parameter names that we're going to keep track of. So these are the parameters to save, and these are the Bayes model parameters. So we want to save theta and omega. Theta is going to be a vector of length 10 because we've got 10 players. We also have to kind of provide a way to generate or just kind of initial values here, okay? And so again, this is strange, but it gets wrapped up in a function. But it's going to be a list of names for kind of the initial parameters. So basically, every parameter that we're going to save is has to have an entry in this list. So I've got theta and omega, and then I just need to create some initial values. Now you have to create your initial values so that they're compatible with the model here. Okay, so here I've got I want 10 random beta values drawn. I just arbitrarily picked 3, 7. It doesn't matter. I just need 10 numbers between 0 and 1. And then omega here, I just need 1 number between 0 and 1. Okay, so this is just a way to kind of specify the original things. Okay, so we're gonna just set a seed, and then we'll run this, and that's it. So we just have to specify the model. I think it's easier just to specify the model this way than to try to factor out all of the different conditional distributions. Okay, so I'm going to go ahead and do this. And it goes and it runs, and it tells all sorts of stuff. It says compiling model graph and all sorts of other stuff. And the values, so observed 5,066, that's kind of related to how many entries I have in Y. Okay, and then the things that it's trying to figure out are the 10 thetas and the omega, and it goes and it samples all of this. Okay, and it's done. And now we can say, all right, what does the resulting model look like? And this is what it outputs. Okay. So let me show you how this compares. So we created our own Gibbs Sampler model, and deleted everything. Oops. Is that what I wanted to do? I did something wrong. Okay, so I've got, let me show you. So this is the result of running the Gibbs sampler that we coded up ourselves over here. And let me just show you the results of running Jags. Okay, so when we coded up our Gibbs sampler ourselves, inside inside my environment, I've got omegas. I've got a whole bunch of omegas, and I ask, just kind of the distribution of the omega values that I have, and it gives me, in the 2.5 percentile, I'm at 0.26. The 50th percentile, I'm at 0.281. And that also lines up in the 97.5 percentile, I'm at 0.301. Okay. And so basically these values here line up right along with kind of the Gibbs sampler that we coded up ourselves. Okay. So this is a good sign that whether I use Jags for Gibbs sampling or whether I kind of coded up myself over here, we're getting kind of consistent results. Okay. I could also kind of just look at, say, for one of the players, player 1, this is kind of the quantiles for this player's theta values. Okay, and again, we can compare this to the results of, so this is player 1, so these would correspond to theta 1. Okay, and so, it's a little bit, again, subject to randomness. But here, the 2.5 percentile is 0.227, 50th percentile is 0.258, 97.5 percentile is 0.290. And so we're looking at the row for theta 1. Okay, row for theta 1, 2.5 percentile is 0.225 versus 0.227. 25th percentile, 0.247, 0.247 up here. 0.258 for the median, 0.258 for the median. 0.268 for the 75th percentile. 0.289 for the 97.5 percentile versus 0.290. Okay, so we're getting consistent results between for kind of estimates of what theta 1 should be. Okay, and we can do this and look at the results for, say, player 2. Okay, player 2. Player 2 has a higher batting average, right? Player 2 has 139 hits out of 493 at bats for kind of an empirical batting average of 0.281. And so their estimates from Jags, 0.252 all the way up to 0.315 also align with what kind of our Gibbs sampler sampled here. So all to say is that even though we didn't specify kind of the posterior distributions and all of these different things that we have to, factor the joint distribution down into, we can run Jags and it performs Gibbs sampling for us. And the results of this are consistent with our results, which is a good sign and gives us confidence in being able to use Jags. Okay. And in fact, if my results did not align with the results from Jags, I would be questioning my own results probably. Okay, I would probably wonder, like, I wonder what I specified in the model that's wrong. And so, and I think that's the hard part with Gibbs sampling, is that you'll write code and stuff, and it's hard to know if you did it 100% correctly, right? So if you can kind of get consistent results, that's always a good sign. Okay, so there's a few things you can do. You can create a plot, and this is just kind of like this summary plot of the different parameters that it has sampled for. So this is kind of like a 80% confidence interval for omega. Omega is the overall parameter that determines what alpha and beta are in our prior distribution. And then we have 10 players, each with their own theta. And these are kind of the confidence intervals here. I don't actually know what all of this stuff up here is. There's something called the trace plot, and it will show you kind of the the traces of kind of the different parameters that it's sampled. So here's omega, and we can see it kind of bounces around. We have 3 colors because there were 3 chains, and basically you just want to see. This is kind of what you want to see. You want to see values looking like they are just independently sampled from the distribution. You don't want to see some kind of clear path that you can follow along or anything like that. Okay, if you see a lot of kind of correlation with itself, then that's it. That's an issue. Okay, and this is the trace plot for, say, player 1's theta value. So that's theta 1, and so on and so forth. Okay, and I think I got to get through a bunch of these. There's 10 theta values. There's also additional plots that can be created. You got to load up these other libraries, okay? And then you take your resulting thing and you have to convert it into an MCMC object, which is basically what this library Coda uses. And so, so you can do that, and you can create. Okay, so here's kind of a trace plot with everything, just showing all of these things. And again, we just want to see random chaos here, and this looks good. This will show you density plots. Here we go. All of the, okay, I don't know what order this is in, but basically showing us the density of kind of each player's theta value. So I don't know why it's in this weird order here, but you know, theta 1 has a peak somewhere around 0.26 and stuff, whereas player 2, who had a better performance in terms of hits and at bats, has a peak centered around, you know, 280, 0.28 and so something like that. Okay, omega looks to be centered around 0.28 and things of that nature. Okay, so those are just some plots there. Does this feel okay? The using of this. All right, let me give you your first quiz answer. First quiz answer for today is A. A as in apple is your first quiz answer. A. Okay, and so I just kind of run all of that. Here is, okay, so here's just a few things to illustrate. So yeah, so these are the individual players, their hits, at bats, and batting averages. And then when we run Jags, these are the results that we get. Okay, and so these are just some of the plots. Oh yes, you can use the values directly. Okay, so you can use the values directly. So after you fit the model, you can the structure of the model. Bayes model fit. It's stored as this huge list inside R. There's a whole bunch of different things. Okay, and one of these, so there's the model itself, the bugs output, okay, which has a whole bunch of stuff, and then there's a bunch of other things. Okay, and so within inside the bugs output, that which itself is a list, there's a few things. Okay, and one of them is you can get the actual values inside sims list. So these are the kind of the simulated values. And so so sims list, we've got the kind of the theta values that we've drawn, and so we can access that directly here. And so I can say from the bugs output, let's look at the simulated list, and from there, let's just look at the theta aspect. And inside R, it's got a structure, theta itself, because we have 10 theta values to sample from, one for each player. It's a matrix, okay? One row for each kind of iteration or each value that it simulated, and then one column for each of the players. So here I'm going to just say, let's take a look at the first player. So I'm going to say all the rows, comma, first player, and we can say, you know, what's the histogram? So here's the histogram. We can see it's centered around 0.26, 0.258, something around there, okay? And then if you wanted to ask a question based on this, if you wanted to do, say, Monte Carlo estimation, and we asked a question like, what's the probability that player 1 will get 2 or 3 hits in the next 10 at-bats, okay? So the answer to that would be, from the binomial distribution would say, you know, what's the probability of getting 2 hits and 10 at-bats with some particular theta value. So we want d binom 2 comma 10 plus d binom 3 comma 10. And here we're going to just throw in different potential theta values, right? So versus, you know, the frequentist approach is we just said theta is equal to 0.27 and we plug that number in, okay? But with the Bayesian approach, we say theta could be any value. Theta could be as low as 0.22. It could be as high as 0.30. It's most likely to be something around 0.26, 0.25, and something around there. And so we just plug in all of our simulated values, and so we take all of our sampled thetas, which we've extracted out of our model results, and we can plug that into H, and then we can take the mean of all of those things, and we get kind of our Monte Carlo estimation there. Is that good? All right. Okay. Thanks for nodding your heads. All right. So so we can go further and specify our model just slightly differently, right? So this looks almost exactly the same, and it pretty much is, except you'll notice here. So if we compare this to a few slides back, okay, here we modeled down here our data is a big matrix. We have one row for each player, and the individual hits, whether it was a hit or an out, a 0 or 1, comes from the Bernoulli. Okay, so here I've got for the number of players, and then within each player, I have a second loop that goes over each at-bat. Here, I don't worry, I don't have anything about at-bats, okay? We're going to just have for each player, okay? And each player, Y now represents the total number of hits, okay? So rather than looking at, say, the outcomes of zeros and ones, we're just going to say there was a total of 118 hits, okay? So that's what the Y's here represent. So rather than zeros and ones, Y just represents the total number of hits. And so we're going to say the total number of hits comes from the binomial distribution, where the parameters are the probability of getting a hit and how many at-bats there were, okay? And so this is where, in order to know what parameters get specified, this is where you kind of need to be able to consult the what do you call it? The model specification here. So the binomial here is P and N, P for the probability and N for your sample size, which I think is a little bit, which is different from the way R specifies it. I think R goes N first and then P. So anyway, you'll need to reference that. Okay, and then but everything else remains the same. Theta comes from a beta distribution with shape parameters alpha and beta, and all of those are determined by omega, which is drawn from the beta. Alpha is determined by omega and k, and these things are kind of pre-specified. Okay, and so I have that entered in R as well. This is model 2, and so I've entered that, and so I can just run that, I provide the list of the values that it's going to use. And here I'm going to create Bayes model 2. And I broke something. Oh, and his number of players. Fix that. Okay, so there it runs, and then we can kind of print the results here. All right, and so these two things, so Bayes model fit 2 and Bayes model fit 1 should be pretty much identical. Okay, and I believe they are. So model fit 2, we should have something very similar for values of omega, ranging from 0.261 to 0.301. Yep. Ranging for theta 1, 0.228. Just ever so slightly different, 0.225 to 0.289. And again, everything's subject to a little bit of randomness because it's Gibbs sampling. So 0.250 to 0.316. You know, if you look at the 50th percentiles, they're still right around the same values, 0.281, 0.257 to 0.281 to 0.256, 255, 2.21. Okay, so very, very similar results that we're getting when we specify it this way. So that's a good thing, good sign. All right, so I'm just kind of showing you some of the other stuff. And then, and again, even though I've kind of switched this up, we don't have to worry about refactoring the entire Gibbs sampler. Okay, so this just talks about the changes that I've made. All right, so the last model I'll show you today is one thing is inside our model specification, we've been saying K is just this arbitrary number 300 when we specify this, okay? And what we can do is we can say, well, you know what? I don't know how I feel about this. I don't know if I feel good about using this number 300, okay? Because this number 300 ultimately determines the alpha and the beta that goes into my prior distribution for theta, right? Because alpha is omega times k minus 2 plus 1, and then beta is 1 minus omega times effectively k, right? So we got 1 minus omega times k minus 2 plus 1. And so whatever number I choose here, 300, 100, 500, that's going to factor into how big my alpha and beta are, because alpha plus beta will add up to k. And so that's going to determine basically how wide my prior distribution is, right? So if k is a big number, we're going to effectively say that prior to looking at the player's individual hits and at bats, you know, this is how much confidence we have in, you know, the width of our distribution, our prior distribution. And then the lower the k is, it's going to be a little bit more spread out. So anyway, in our third model, everything else is exactly the same as the second model, except this time, rather than specifying directly k is 300, I'm going to say k comes from some random distribution, okay? Now, I've arbitrarily chosen a gamma distribution with these parameters, okay? Now, the reason why I chose this, and again, somebody could come along and say, I want a completely different value distribution, hyper prior distribution for k, and they could probably justify it. Okay, this is what the hyper gamma 2, 0.008 distribution looks like. Okay, it starts at 0 and it has a very long tail. This keeps going to like 1,000 and so on and so forth, and it's got you've got high values, basically anywhere from like 50 to like 400. Okay, so it's basically saying any value for what you know, k could be really any value from say 50 to 400 or 500. there's a higher peak there. Okay, I mean it could be 800, it could be 1,000, but those are lower probabilities. And k is also just, it's not going to be 1 or 0 either. So so this is just kind of something where I've got higher densities around, you know, say values 50 to 500. And the number that we've chosen, 300, fits somewhere comfortably somewhere in there. But it really could be anything. Now, if somebody wants to pick a different distribution, if they want to say k comes from a normal distribution centered at 300 with a standard deviation of 100 or something, that's probably also fine. Okay, I think they would also have to. You can do this, but you can kind of set limits on it. So you can say, but on the lower, the smallest that k could be will be 1 or something like that. So so you'd say it comes from a normal distribution with a mean of 300 and a standard deviation of 100. But we're going to put hard limits on it, and we'll say that k is not allowed to be smaller than 1, because that will cause problems in our model specification if k turns out to be a number smaller than, well, less than 0. Okay, so anyway, I'll run it this way. So here I'm going to kind of just redefine my model, but this time specifying that k comes from a gamma distribution, and all of this. And now, as far as parameters that I need to keep track of, I have to add k into my list of parameters, okay, because k is now being modeled randomly. And here I also need to, if I add k to my list of model parameters, I also need to add k to my initialized values. And so here, it doesn't matter, but I guess I did 10, I should probably have it match up to 0.008. Okay, so we'll run all of that. Okay, and then so here I will run it, run my model with Jags. It's complaining, oh, number of players, sorry. Okay, so it runs, and then and let's take a look. Okay, so let's compare this to let's compare this to. So if we look at the results for, say, omega, so this one is where we've modeled k, and we can see when we model k, we do get in the 50th percentile a number kind of close to 300, okay? But it could really be actually any number as low as 100 or as high as 740, it looks like, for 2.5 to 97.5 percentile. But kind of, you know, over half of the values are between, you know, 211 and 413 or something. Okay, so what kind of values of omega are we getting? We're going from 2.259 to 0.301, which is very similar to what we did when we specified k is equal to 300. We can look at the values of theta. Theta 1 goes from 0.224 to 0.291, and theta 1 here also, you know, similarly goes from 0.228 to 0.290. So this one has a little bit more spread, which makes a little bit more sense. What makes sense here, because over here, our prior distribution is fixed at 300, and over here, our prior distribution, you know, that k is not fixed at 300. It could be lower, it could be higher. So we're going to end up having, you know, just a little bit more spread, just a tiny bit more spread in kind of the resulting values that we fit. All right. So that is, that's just a very, very, very brief intro into using Jags for Gibbs sampling here, okay? Jags is a very powerful tool. You can look up, you know, if you go online and you just type in Jags tutorial, R and Jags tutorial and things like that, there will be tons of different hits and resources. All of them will probably be in the context of Bayesian modeling and hierarchical models, Bayes hierarchical models. But again, very powerful tool that really allows you to kind of create these samples of values, which can then be used in inference questions like Monte Carlo estimation and stuff like that, for I don't know, different kinds of things here. Okay, and it really does simplify our life in that we don't have to do the math to factor out the model into conditional distributions, which is a huge this is factoring it into these conditional distributions can be challenging, but fortunately for us, this handles that. I mean, Gibbs sampling in of itself is designed for kind of these hierarchical models, in that the hierarchical models simplify the conditional distribution factoring. Okay, let's we'll call it there. So let me give you your last 2 quiz answers. I know I haven't released the last homework yet. I'm still writing it up and editing it. So I appreciate your patience with the final homework. But I'll get that up and I'll make sure you guys have plenty of time to complete it. Okay, last 2 quiz answers for today are C and E. C as in cat, E as in elephant. Okay, C as in cat, E as in elephant for the last 2 quiz answers. The yeah, that's it. I think this week you'll get course evaluation emails and stuff, and so if I could ask you a favor to fill those out, that will be helpful for me. I'm actually scheduled to be reviewed for a promotion this year, so your whatever you call it, your evaluations get factored into there, and so appreciate that. Don't hesitate to give me constructive feedback or any kind of criticisms that you have. I read them and I take them to heart, and but it's just more helpful if you're specific. Okay, so if you can specifically say, your covering of this topic was very confusing, or something like that, rather than just saying the lectures were confusing overall in general. That's not so helpful. But if you're able to say, lecture 7.1 or whatever it was, this week in this topic, I had trouble with this, or this specific policy you have in the class I don't like, and things like that. That's always more helpful, so I can kind of pinpoint what needs to be changed and what needs to be improved there. Okay, so we'll end here, and we'll see you guys on Friday.